Good evening, everyone. So, today we are going to discuss some of the important material testing methods, including both mechanical and analytical methods. So, in mechanical testing methods, these are the three important mechanical testing methods for testing materials: tensile test, impact test, and hardness test. But these are first one is tensile test. This is a mechanical test in which a material specimen is pulled until fracture. The specimen is pulled until fracture to study its properties, especially important characteristics like ultimate tensile strength, yield strength, and percentage elongation properties. Okay, so this is the universal testing machine which is used for conducting tensile test. It has two crossheads, one is fixed and one is movable. In between these two crossheads, we will be loading the specimen, which is to be pulled and tested. And to this attached are sensors to measure stress and strain. Okay, which is connected to a system which will be giving us the stress strain curve after completion of the test. For doing tensile test, we need special specimens. So we cannot test the material as it is on the testing machine. So for that, we need to machine the material. We will be machining the finished product to make suitable tensile testing specimen, which has two broad shoulders and a narrow gauge section. Okay. So the broad sections are for used for clamping the specimen to the testing machine. Okay. So this is a schematic representation of how the test is conducted and the specimen is loaded on the testing machine. So the specimen is clamped between the fixed and moving head of the testing machine, and an extensometer will be attached to the specimen to measure the strain or elongation. And also a load cell will be attached to the machine which will be measuring the load applied. From the load and strain, we will be getting the stress strain curve at the end. Before loading the specimen, see this is the specimen. Before loading the specimen to the machine, we need to make gauge length markings on the specimen. At see this narrow area is called the gauge section. On the gauge section, we put two dots, probably usually 50 mm apart. This will be used for calculating percentage elongation after the completion of the test. So before loading, we need to put two marks on the gauge section, 50 mm apart. Okay, and then this will be loaded and the test begins. So what will happen during the test? As I told you, the specimen will be loaded here, and then the moving head will start pulling the specimen. At that time, both stress and strain are measured and displayed on the computer screen. When the specimen breaks, the test ends. At the time, we will get the stress strain curve of that particular material. From the stress strain curve, we get all the important information we needed. Look at this. This is the first stage when the specimen is pulled up to the yield strength. So when the specimen is pulled when the load is within the yield strength of the material, the specimen will elongate elastically. The specimen will be undergoing elongation or elastic elongation. What is elastic elongation? When the load is removed, the specimen will go back to its original dimension. Suppose you started with 12 inch of the length of specimen, and during the pulling it elongated up to 12.5 inches, and then if you remove the load, it will go back exactly to 12 inches. This is elastic elongation. This happens only up to the yield strength or yield point of the material. After that, what will happen? Then starts the plastic strain or the plastic elongation. After yield strength, the material continues to elongate, but this time plastically, not elastically. What is plastic elongation? Yeah, even yeah, that is a permanent deformation. Even if you remove the load, that deformation will stay. It will not go back to its initial stage. So from yield strength up to ultimate tensile strength, this is the highest load. The highest load is the ultimate tensile strength. Highest load the material can withstand before breakage is called ultimate tensile strength. So from yield strength up to ultimate tensile strength, the material undergoes uniform plastic deformation. It is plastic but yet uniform. That you can see here. So the material now undergoes uniform plastic deformation up to ultimate tensile strength point. And what happens at the ultimate tensile strength point? A phenomenon called necking will begin. A phenomenon called necking will begin. Necking means now until this point the deformation was uniform. Even though it was plastic, it was uniform. But at the ultimate tensile strength point, the elongation or the deformation becomes non-uniform. Suddenly, the width decreases only at a particular point, at the middle point. The narrowing will be happening only at the middle point, non-uniformly. And immediately it fractures. Once necking starts, the next moment the specimen fractures and the test ends. So you can see that after the necking begins, the load is very low load is required. Further for a further elongation, the load required is lower than before. That is because of the necking. The material weakens too much, and then you can see there is a drop in the curve, and this is the fracture point where it breaks. Okay, so these details we'll get, and from this stress strain curve, we get the important characteristics we need. First one is ultimate tensile strength. Ultimate tensile strength is the maximum stress a material can withstand before failure. Next one is yield strength. This is especially important in case of bolts and all. So up to yield strength or yield point, the bolt will extend elastically. That elasticity is the stress load. That elasticity is the thing that holds the joining parts together. If you tighten the bolt beyond its yield point, what will happen? That will elongate plastically. So the joint loosening will happen and failure will follow. So this is yield point is also very important, especially in case of things like bolts and all. Then comes percentage elongation. Percentage elongation is an indicator of ductility. How ductile is the material? For this only, we initially made gauge length marking at the beginning. On the specimen, we put two dots at 50 mm apart. Now after breakage, we will just join them together and measure the distance between those dots again. So that gives a elongation length. So from the initial 50 mm, how much it has elongated before breakage. This will give us percentage elongation. The more percentage elongation is there, that means the material is more ductile. Okay. So this is all about tensile test. Okay. Final, initial and final. That's it. In between the breakage, all the stages crosses. Elastic elongation, plastic and non-uniform plastic, everything happens. And then it breaks. Then afterwards what we'll do? Suppose the specimen breaks and now we again just keep them together and measure the distance between those two dots we put earlier. That will give us how much elongation happened before breakage. Okay, that is percentage elongation. So now moving on to the next mechanical test. This is impact test. Impact test is used to determine the toughness of a material, that is, its ability to absorb energy during sudden loading or shock. Impact test is used to measure the toughness of the material. What is toughness? Its ability to absorb sudden shocks or sudden loading. Just like in case of our couplers, CBC couplers and all. Sudden heating and cooling, it happens there. So it is supposed to have high impact strength. So we do impact test for checking the impact strength of the material. For this, what we usually do is we make a specimen out of the material. Again, just like in case of tensile test, here also we need to make specially designed test specimen. The test specimen is usually a bar with a notch in it. A notch artificial cut will be there, which will simulate an actual crack or a stress razor. Okay. So what will happen? We will load the specimen onto the impact testing machine, which is actually it is a very simple setup. It is actually a pendulum hammer. It is a pendulum hammer. So the specimen will be loaded and then the pendulum hammer will be released onto it, which when hits the specimen breaks into pieces, two pieces. So the energy absorbed during that hit, that is what is the impact energy that will be measured. Okay. So I'll read it. In this test, a notched specimen is struck with a pendulum hammer and the energy absorbed in breaking the specimen is measured. That is impact energy. From impact energy, we can calculate impact strength. Impact energy, impact strength is impact energy per area at the notch. I will explain this part in the next session. See, look at this one. This is the impact testing machine. You can see a pendulum hammer which has a particular weight, mass, and then here is the position where we are going to load the test specimen, and this is the notched test specimen. A notched test specimen. There is a bar here, and then there is a notch artificially made cut on it, which will act as a stress razor. In real situation, cracks may be there, or some design aspect may be there, where stress concentration may happen. So for simulating that, we will put a notch on this one. And now, see, after the test, the specimen breaks at the notch into two pieces. Okay. So before going to the different types of things, I will tell you a simple thing I will explain. Actually, what is happening here is we place the specimen here and release the pendulum. Before releasing the pendulum, the height of the pendulum and the mass of pendulum is noted, so that we can calculate the potential energy, mgh. Potential energy is mgh. So after the pendulum is released, it goes, hit and swing through it. It will swing to the other side. But this time what will happen? The height of the swing will be less than the initial height. Why it happens? Suppose if there was no specimen in between and you release a free pendulum from here, and there are no, suppose there are no friction forces or anything, automatically what will happen? It would go up to the same height on the opposite side. But en route, it hits the specimen and breaks it, and for that it spends some amount of energy. Some amount of energy was used to break the specimen. So what will happen? The pendulum can't raise up to the same initial height. So there is a energy difference. That energy difference is the impact energy. That is the energy absorbed by the specimen before breaking. Okay. So from that impact energy, with this formula we can calculate impact strength. Impact energy divided by area at the notch. What is area at the notch? The cross sectional area. That is what we are talking about here. At the notch means, there is a 2 mm notch here. So from here, suppose the thickness of the specimen is actually 10 mm. 10 mm this way, 10 mm that way, and here it is 55 mm. So here 2 mm notch is there, so the thickness decreases to 8 mm. So 8 into 10, that area only we will take. So that impact strength is calculated by dividing the impact energy with the area under the notch, area at the notch or at the stress razor. Okay. So from this we can get the impact strength of the material. Now there are two different types of impact test, namely Charpy test and ISO test. These two tests are actually used for testing different types of materials. For our purpose, most of our steel items, railway components, etc., for that we use Charpy test. And for testing plastic and other fiber materials and all, we use ISO test. The total mechanism is same only, but the specimen design and the method of loading the specimen are different. In Charpy test, the specimen size is 55 mm. The other two dimensions are 10 into 10. Okay, and the specimen will be loaded horizontally. In Charpy test, the specimen will be loaded on the machine horizontally, and the impact happens from opposite side of the notch. But in ISO test, the specimen is loaded vertically and as a cantilever. That means only one side support will be there. In case of Charpy, both sides are supported. This is most of the practical cases, like our rail or anything. Most of them are always supported both sides. That's why we are using this Charpy test for metal testing. While for plastic testing and all, only that crack is very important. Even crack propagation is not important in case of plastic. If there is a crack, it will immediately fill. But in metals, the crack will take time to propagate and all. Okay. So here more importance is given to the notch, and the load will be applied from the same side of the notch. You are going to hit from this side. See, here we are hitting from the opposite side of the notch. So this is the basic difference between Charpy and ISO test. Okay. And in our case, most of the steel and the other metals are tested using Charpy. During the process, how much energy is absorbed. Based on that, we can find the impact strength of that particular material. So this is impact test. This we have already explained. Impact test shows how a material behaves under sudden loading, whether it absorbs energy or absorbs considerable amount of energy, or it fractures immediately, or it is brittle. Okay, so this gives us brittleness of the material. Now comes to hardness test. So this is very important material testing method, mechanical test, which gives us a lot of clue regarding the quality of the material. For that, we need to do hardness test on materials. There are three types of hardness test: Brinell, Rockwell, and Vickers. First one is Brinell hardness test. In Brinell, a hardened steel ball. In Brinell hardness test, what we will do? We will load the material or the specimen onto the hardness tester, and we will apply a steel ball. This is the Brinell hardness tester. Here is where we will load the specimen. So we keep the specimen here and apply a particular load through a hardened steel ball of 10 mm. And when the load is applied, the hardened steel ball will plunge onto the material, and when the load is applied on the behind the ball, what will happen? One indentation will be formed. There will be one indentation formed on the material, and since it is a steel ball, the indentation will be a circular shaped one. So we can measure the this one. See, look at that. It will be like that. There will be an indentation here, and we can measure the diameter of the indentation. From the diameter of the indentation, we can calculate the hardness number, Brinell hardness number. So the formula is load on the ball divided by area of indentation made by the ball. So we need to calculate the area of the indentation and whatever load was applied on the ball. But actually, in practical scenario, what we will do? We have ready reference charts for Brinell hardness number. Almost all hardness numbers are like that only. You can take the diameter, you can measure the diameter of the indentation, and from that diameter, you can directly refer a chart to get the hardness number. So, the main point here is the indenter is a hardened steel ball or tungsten carbide ball in some cases. For very high hard materials, we have to use tungsten carbide ball. Most in our shed, we are using only hardened steel bar of 10 diameter. Okay. Next is Rockwell hardness test. Rockwell hardness test is performed by pressing a diamond cone or steel ball indenter into the specimen under specified load. So actually, all the three hardness testing methods are having same mechanism. There will be an indenter and a load will be applied. We will get an indentation. Only thing, the shape and the material of the indenter will be different from one method to another. For Brinell, it is a 10 hardened steel ball. For Rockwell, it will be either a 1 by 16-inch steel ball or a diamond So, in this one difference is that the Rockwell hardness means you need not measure the diameter of the indentation. Here, the depth of the indentation is considered. So, how far the diamond or the steel ball penetrates into the material. From that, we can get the hardness value. So, in this case, this is a direct reading method. See, if you put the material here and do the test, you can directly read the hardness on the Rockwell machine. So, this is the simplest of all the three. Rockwell hardness test is the simplest of all the three. You can directly put the material and take the hardness directly from the dial. Okay. And next is, see, advantages of Rockwell. As I told you, it is the simplest thing, fast and simple, direct reading of hardness value, suitable for bulk testing. Because if you have to test a lot of items, you can simply keep testing because you need not refer any chart, you need not calculate area, anything. Direct reading will be available from Rockwell machine. But the problem is it is less accurate than Brinell and Vickers. It's not that accurate. Next comes Vickers hardness test. Again, here we are using a diamond indenter. Diamond pyramid, inverted pyramid, indenter will be here. And here also, we have to measure the diameter or the diagonals of the indentation. Since it is a diamond indenter, we get a square indentation and we measure both the diagonals. And the average diagonal is used for calculating the hardness. Here also we have the equation applied load per area of indentation, but still here also we have reference charts. ASTM reference charts are there from which we can get the reading directly. Okay. So the main difference between all the three were actually the load range. Not only the difference in indenters, load range was different. In case of Brinell, the load range is 500 to 3000 kilograms. In Brinell hardness testing, the load applied is between 500 kilograms to 3000 kilograms. So this can be used over very tough materials. Okay. And also thin materials cannot be tested. Thin and soft materials cannot be tested because of the very high load applied. And in case of Rockwell, we have around 60 to 150 kg load. Okay. And in Vickers, we have again very low, 5 to 50 kg. In Vickers is the one where very low loads are used. Even micro Vickers are available, where 100 to 300 grams can be applied as load for testing soft materials. So these are the three major hardness testing methods.